Students, in the first session of wave optics, we tried to understand the Huygens principle and we saw that the macroscopic phenomena can also be explained successfully using wave theory. Among the microscopic phenomena, first we will take up the interference. In the course of class 11, you might recall in the chapter of waves and oscillations, we read about the superposition principle of waves. Besides standing or stationary wave and beat, the interference is also the consequence of superposition of waves. Standing wave and beat are the results of superposition of mechanical waves, while interference is the result of superposition of electromagnetic waves. Let us recall the superposition principle first. The principle states that the resultant displacement of a particle of medium acted upon by the two or more waves simultaneously is the vector sum of the displacements of the same particle due to individual waves at that instant. That is, y is equal to y1 plus y2 plus y3 and so on. For two waves, this relation is y is equal to y1 plus y2. When crest of one wave falls on crest of the other, the amplitude of the resultant wave is the sum of the amplitudes of individual waves. But when crest of one wave falls on trough of the other wave, the amplitude of the resultant wave is the difference of that of the individual waves. That you can see in the plots of displacement with time as shown in the diagrams. If now the amplitude of two waves are equal or nearly equal, that is y1 is equal to y2, then the amplitude of resultant wave in the first superposition is double and it is 0 in the second. The first type is called constructive superposition while the other is called destructive superposition. Interference is actually a special situation of superposition. When two waves from coherent sources of light having same or nearly equal amplitude superimpose, then the resultant amplitude in the region of superposition is different from that due to individual waves. This modification in the distribution of intensity in the region of superposition is called interference. We can say that interference of light is the phenomenon of redistribution of light energy in the medium on account of superposition of light waves from two coherent sources. What is coherent sources of light? The sources of light which emit continuous light waves of the same wavelength or same frequency and in same phase or having a constant phase difference are called coherent sources. In interference, the points where the resultant intensity of light is maximum, then it is constructive interference, which is bright region, and the points where the resultant intensity of light is minimum, then it is called destructive interference, which is the dark region. Interference does not mean any loss of energy. Instead, there is only redistribution of energy. The light energy being transferred from dark region to the bright region. Let us now list up the conditions for interference of light waves, and these are: number 1, two waves must be coherent. Number 2, two waves must have same frequency. Number 3, the amplitude of two waves must be same or nearly same. Number 4, waves must travel along the same line or along different lines having small inclination. For fulfilling these conditions, Thomas Young provided an experimental setup in which a narrow slit of width about 1 millimeter is illuminated by a monochromatic source of light. At a distance of about 10 centimeter from this source, S, two fine slits A and B at a separation of about 0.5 millimeter are symmetrically placed, through which two separate waves are derived. Since the source of both waves from A and B is same, so the condition of two coherent sources is fulfilled. Hence, the interference pattern is observed on the screen placed at about 2 meter. The interference pattern consists of alternate bright and dark bands running parallel to the lengths of the slits. These equidistant alternate bright and dark bands are called interference fringes. On the basis of wave theory, we can find the mathematical expressions for the condition of interference. According to Huygens' principle, the monochromatic light source illuminating slit S sends out cylindrical wave fronts which reach to the slits A and B simultaneously. So A and B become source of secondary wavelets. Thus, two waves of same amplitude and same frequency with zero phase difference are given out by the slits A and B. You can see in the diagram, the continuous semicircles represent crests and dotted semicircles represent trough of the waves. On superposition of waves, interference pattern appears on screen. The constructive interference is represented by dots, where crest of one wave falls on crest of the other and trough of one wave falls on trough of the other wave, hence giving maximum intensity of light in these positions. Similarly, the destructive interference is represented by crosses, where crest of one wave falls on trough of the other and vice versa, giving minimum intensity of light in these positions. Thus, at C, E and G, bright fringes appear, while at D and F, dark fringes appear. The bright and dark fringes are alternately equispaced. Let us derive the conditions for interference by analytical treatment. The waves from two coherent light sources be represented by y1 is equal to a sin omega t and y2 is equal to b sin omega t plus phi, where a and b are the amplitudes of the two waves and phi is the constant phase difference between the two waves. As you know, this phase is the angle by which the second wave leads the first wave. According to superposition principle, the displacement of the resultant is given as y is equal to y1 plus y2, which is equal to a sin omega t plus b sin omega t plus phi, or y is equal to a sin omega t plus b times sin omega t into cos phi plus cos omega t into sin phi. Taking out sin omega t common and cos omega t outside, the relation becomes y is equal to sin omega t into a plus b cos phi plus cos omega t into b sin phi, which can also be written as y is equal to sin omega t into r cos theta plus cos omega t into r sin theta, where r cos theta is equal to a plus b cos phi and r sin theta is equal to b sin phi, so that r is equal to under root a square plus b square plus 2ab cos phi. In the expression of y, taking out r common, y becomes equal to r times sin omega t into cos theta plus cos omega t into sin theta, which gives y is equal to r sine omega t plus theta. The resultant wave is a harmonic wave of amplitude r, which is given by equation 1. As the resultant intensity is directly proportional to the square of the amplitude of resultant wave, that is, I is proportional to r square, therefore intensity I is equal to a square plus b square plus 2ab cos phi. For constructive interference, I should be maximum, that is cos phi is equal to 1 or phi is equal to 2n pi, where n is equal to 0, 1, 2 and so on. And the path difference, which is equal to lambda by 2 pi times the phase difference, that is delta x is equal to lambda by 2 pi into phi. Hence path difference delta x is equal to lambda by 2 pi into 2n pi, or delta x is equal to n lambda. Now we can summarize the condition. For constructive interference at a point, the phase difference between the two waves should be either 0 or even multiple of pi, and path difference should be integral multiple of the wavelength. For destructive interference, I should be minimum, that is cos phi is equal to minus 1, or phi is equal to 2n minus 1 pi, where n is equal to 1, 2, 3 and so on. Therefore, path difference delta x is equal to lambda by 2 pi into 2n minus 1 into pi, or delta x is equal to 2n minus 1 into lambda by 2. The condition is then summarized as: for destructive interference at a point, the phase difference between the two waves should be an odd multiple of pi, or the path difference should be an odd multiple of half of the wavelength. Students, you keep the conditions in your memory, as in the next session, while finding out the width of the fringes in interference pattern, we have to use them. So see you in the next class.